In this video of Module 3, we're going to be talking about the momentum flux correction factor, and then go on and start talking about the frictionless flow and the Bernoulli equation. So to start with, last video we had talked about linear momentum, and we derived some equations for linear momentum. And we had looked at a system where we only had uniform flow or 1D flow through a duct, for example. Now, if we have flow in a duct and we want to analyze a flow in a duct that has non-uniform, we have to sort of correct our equation for momentum flux. Okay, remember momentum flux is capital M dot. And for a flow that is uniform, if we remember, so for a uniform flow, we had the equation as follows. We had an equation that said that the integral of u times rho times v dot n dA is equal to m dot v, which is equal to rho a v squared. And that was the equation for uniform flow. Now, if we have a flow that is non-uniform, we need to be able to calculate the momentum flux for a flow that would look like this in a duct instead of a uniform flow that has the same velocity throughout the area that it's crossing. And for this, we're going to create a correction factor for this flow. We're going to create a correction factor called zeta. So we're going to use a correction factor called zeta. Okay, and the zeta symbol looks something like this. Okay, and we can say that zeta is greater than 1, greater than or equal to 1, and this zeta symbol is going to account for speed variation along the section. So it's essentially a correction factor that we're going to use to account for the variation. And then experimentally, we can figure out what this value would be using typical duct experiments and figuring out how we can solve for the velocity and go from there, essentially. So what we can say is that if we have a pipe flow in one direction, okay, in the x direction, we can say that the equation above can be written as density times the integral of u squared dA, okay, assuming we have flow in this direction and we have incompressible flow, so density can come out of the integral. And this would be equal to, now, instead of having it equal to just m dot times v total, it's actually going to be equal to zeta times m dot times velocity average. So for non-uniform, we need to use our velocity average, and we're going to use that zeta in front as a correction factor. And so we can write that this is also equal to zeta times rho a v squared average. So it's the average velocity. And experimentally, we can find that for laminar flows, so if we remember what we had defined as laminar flow is sort of low speed flow with a very structured flow. Okay, laminar flow is usually structured. For laminar flow, we can say that zeta is usually equal to 4/3. Okay, And there's also a formula in your book for turbulent flow and a table for turbulent flow given a certain amount of given like values for velocity. You can find it for turbulent flow at different velocities. Now, for turbulent flows, we're actually usually going to neglect this term zeta. So for turbulent flows, we neglect zeta. And the reason we neglect zeta is because for turbulent flows, the value of zeta is extremely close to 1. It's usually just above 1. So it's the highest value that we can usually find is 1.037, which means there's a 4% difference, okay, 1 or 3.7% difference above. So we usually just neglect it. Now, if you do want to have it so that you make sure that you get the right answer and you have time to do a problem, you could use it, but in this class, we're going to neglect it. So for turbulent flows, we can neglect this zeta. Now for laminar flows, if we're told we have a non-uniform flow, we should use a zeta of 4/3 to correct our equation. So if you're given a flow and you're told in a question that your flow is laminar and that you do not have a 1D inlet or outlet, you should use that zeta correction factor and the velocity average. Okay, so let's do a quick summary of our linear momentum and momentum in general. So this is from the last video and this video. So we can say that for a momentum summary, we can say that clearly vectors are more complicated than scalar. So for vectors, we actually have to figure out the direction of our forces and the direction of our velocities. So in momentum, our force is going to be in the x, y, and z direction. So we're going to have 3 equations and we're going to have to separate them into x, y, and z. Now, mass is more of a scalar quantity. So the mass flow is a scalar quantity. We just go in or out, and that's it. We don't really need to know what direction the mass is going in. However, we need to figure out what the velocity is. So we need to use this vector velocity and make sure that we always get it correct. So for velocity, we usually have the term rho times velocity dot n, and we know that out is going to be positive and in is going to be negative. Okay, so we know that the velocity into a surface is usually going to be negative and the velocity out of a surface is going to make the mass positive. Okay, the mass flow positive. The other solutions that we can say and the other conclusions that we can have from this is that 1D is amazing for us as engineers. If we can assume 1D, it makes it very simple. We just have a surface that goes in and out and it's very, very easy. And we just would make sure that we choose an inlet or outlet. And usually that inlet or outlet is going to be normal to the flow. So if we choose an inlet or outlet that's normal to the flow and we can assume 1D, it makes our problem very easy. Okay, and your book on page 160 has some linear momentum tips that can be applied. So I'll let you read those, but you can read those tips if you want to have a little bit more information on how to solve the problems. Okay, so the next thing we're going to go through is look at a special case of our linear momentum relation, and that is if we have frictionless flow, which obviously does not exist in real life, but can help us solve some initial problems much more easily and then apply some correction factors down the line. So frictionless flow, we're actually going to look at Bernoulli's equation. And most of you have probably heard this equation, but where does it come from? So we're going to look at where it comes from. So Bernoulli's equation is a relation that can be derived between pressure, velocity, and height, okay, or elevation. Z, remember, is the term for elevation. And so this Bernoulli relation is going to help us understand the comparisons that we can make between pressure, velocity, and height, essentially. And I'm going to write it down again, but this is only good for frictionless flows. So we can only use it for frictionless flows. If there's friction, then it doesn't work. Okay, and what we're going to do in order to solve this problem is we're going to have to define a streamline. So we're going to look at the flow a little bit differently. We're not going to look at a control volume, but now we're just going to look at a streamline and follow along that streamline. So we're going to follow a streamline and analyze the streamline as we move along the line, essentially. So a streamline in a pipe, for example, that goes with a 90-degree bend would follow a particle that moves along the system if there was flow from one side to the other, for example. Okay, so it's just following a line of stream, essentially, or following a line where a particle is moving. Now, we know that for unsteady flow along a streamline, we can say that, and I'm not going to derive the whole equation because you can see the derivation in your textbook, but and you can derive this equation from the change in forces and then making the change in forces equal to 0. So you can derive this from linear momentum equation, but we're just going to be looking at the final solution, essentially. So we can say that for an unsteady flow, along a streamline, our equation actually simplifies to something like this. So we have that the integral from, let's say, point 1 would be here, point 2 would be here in our streamline. Okay, we're just going to take a simple streamline, and we're going to say that this is equal to integral from 1 to 2 of the change in velocity with time multiplied by ds plus the integral from 1 to 2 of dp over density plus 1/2 times v2 squared minus v1 squared, so the change in velocity between the 2 points, plus g z2 minus z1. And essentially these two integrals here, so to evaluate these integrals, we have to estimate the unsteady effect. So if the flow is unsteady, meaning that it's not constant with time, we need to figure out a way to estimate this unsteady effect. Okay, so I'm going to write to evaluate integrals, we need to estimate the unsteady effect. So we need to have some sort of reading as to how the system is unsteady. So we have to estimate the system unsteady effect, the unsteady effect coming from the system. So one term is dv over dt, so the change in velocity with time, and the other term is we have to know about the variation of density with pressure. So we need to come up with relations for the variation of density with pressure, and we need to know how the velocity changes with time. Now, how do we simplify this equation and how do we make it work better? And this is all equal to 0. Okay, so along a streamline, this is all equal to 0. So the equation shows all this left side is equal to a value of 0 because the sum of the forces is equal to 0. And working through the equation, we get that essentially the forces cancel along a streamline completely. So if we now say we have a problem with steady flow and an incompressible problem, we can now simplify our problem. So if we have steady flow, we can say that the change in velocity with time is going to be equal to 0. So that doesn't mean that the velocity between point 1 and point 2 might not be different, but we're saying that over time, the velocity coming in and the velocity coming out is always the same, okay? The pipe flow is always, for example, if it's a pipe, the flow is always coming in at 2 meters per second and always exiting at 4 meters per second. It doesn't change with time, okay? An example of a flow that would change with time would be if you're filling up your bathtub and you're changing the pressure of the water all the time, you can change the velocity of the water coming in, and that would be a system where you would have unsteady flow. Now, you would need to have an equation of how your velocity is changing over time, which sometimes is very complex if it's something that is created completely randomly. So it's harder to analyze. But if we have steady flow, which is most of our examples, and most of the problems that you're going to be faced with as an engineer is usually steady flow. So for example, they'll give you an example of a steady flow is we have a steady flow going through a dam and we need to figure out what our pressure along the streamline is or what our velocity along the streamline is. So usually we're going to have steady flow in a dam. Okay, we have a certain amount of water at the top, a certain amount of water at the bottom, and we have a tube going through a turbine or something to power and get some electricity. Okay, so usually the examples that we're going to have and examples in the real world deal with steady flow more than anything else. Now, if we assume that it's also incompressible, so if we have water or something, we can usually assume that it's incompressible, except if we're at extremely high pressures, which is not the case in most cases. We can now simplify our problem and rewrite the integral of dp over rho. We can write it as p2 minus p1 over rho because we can take rho essentially out of the integral, and then we just have the integral from 1 to 2 of dp, which is p2 minus p1. So we have a full equation that looks something like this now. So it's p2 minus p1 over rho plus 1/2 v2 minus v1 both squared times g z2 minus z1 is equal to 0. And so we can write, if we separate all the terms of number 1 and 2, we can actually write this as an equation with all ones on one side and all the twos on the other side. So we're left with something that looks like this. P1 over rho plus 1/2 V1 squared plus GZ1 is equal to P2 over rho plus 1/2 V2 squared plus GZ2. And this is equal to a constant. And this constant is equal to a constant along a streamline. So this is along a streamline. So that means that if you pick any point along a streamline, such as in our example above, we had the streamline in the middle. So if you pick any point on the streamline, like point 3, for example, you can apply this equation as long as it's a system that has incompressible flow, that has steady flow, and that is inviscid, or it has no viscosity. Okay, it's a frictionless flow. Okay, so there's a lot of conditions to this, but we're going to be able to use it for a system that goes along a streamline. And one more assumption that we have to make in this is, another assumption that we have to make is that it assumes that there is no energy due to heat or work. So it narrows down our problem quite a bit due to the fact that we are assuming that there's no heat or work. We're assuming that it's along a streamline. We're assuming that we have frictionless flow, and we're also assuming that we have steady flow. So there's a lot of different things that are being assumed. But actually, there's a lot of cases where this actually works well and can be used to solve flow through a pipe, usually, okay, or flow with elevation differences in a pipe. Now, in many incompressible flows too, and this is not in all, but in many of the incompressible flows, we can go even further. We can say that delta Z is negligible. Okay, so this is not always the case, but delta Z is negligible in many incompressible flows, especially if the change in height is very small. Okay, the amount of energy that comes from pressure and the velocity terms is much higher than the change in height, especially if the change in height is 0.5 meter or 1 meter. If the change in height is bigger, then it can have a bigger effect. And if it's negligible, we can actually simplify this equation for some problems to be P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared is equal to P0, which is equal to constant. Okay, so we simplified the equation, and what we did is we multiplied the equation through by density. So we multiplied by density all the terms so that we could get rid of the P1 over density. And this term can be called P0. So we created a new term called P0. So P0 is actually called the stagnation pressure. So we call this term the stagnation pressure. And what this stagnation pressure is essentially the pressure when velocity is 0 Okay, so when the velocity is 0, the pressure increases. The more velocity you have, the less the pressure is. And we can call this the highest pressure within a flow. It is also the highest pressure within a flow. And in the equation above, we can say that P1 and P2 are called static pressures. And a static pressure is just the pressure if nothing was moving. It's just a static pressure. And the second term, 1/2 rho v squared, is also in units of pascals or pressure, is called the dynamic pressure. It's the pressure due to the velocity created, due to the velocity of the fluid. Okay? And what a pedostatic tube does, so we can define what a pedostatic tube is, but a pedostatic tube can be used to measure P0 minus P1. And P0 minus P1 means that this is equal to essentially the dynamic pressure. And if we know the density of the fluid, we can use a pedostatic tube to find velocity, essentially. Now, what is a pedostatic tube? A pedostatic tube is a tube that looks like this. So let's say we have a flow. And inside this flow, we have a tube like this. And the streamline is moving along this line here. Okay, and the flow keeps going around here. Okay, but the fluid goes here. We actually can use this pedo tube to figure out the amount of pressure that is in the flow, so we can find the total pressure, P0, okay, which is called the stagnation pressure, and we can subtract our static pressure from the system, and therefore we can find the velocity of our flow. So we'll go through how this can actually work and how we can make this work in an example given. Okay, so if you don't know what it looks like, just look up pedostatic tube. But essentially what a pedostatic tube is used for, it's used on airplanes, it's used on many different applications. We can find the velocity of flow by converting the flow to 0 velocity and using the height of this column to figure out, okay, we have this much pressure in the system, so we can find our velocity of our flow. We decelerate the flow until we have essentially 0 velocity. And we can show in a diagram how the three terms of our Bernoulli equation, so our Bernoulli equation that we're always going to be using most of the time is going to be this one right here. And we can show how we can actually use this equation in terms of a graphical representation. So I'm going to copy over a diagram and show you what this would look like in terms of a graphical representation. So we have here a system that shows us two different points, and we have flow going up. Okay, so we have flow going up, we have point 1 and point 2, and point 1 can be said to be around here, and point 2 can be said to be around here. Okay, and we see that we can actually create a height measurement for the system. So if we remember, our equation is, so our equation for the Bernoulli equation is P1 over rho plus 1/2 V1 squared plus GZ1 is equal to a constant, okay, which is also equal to P2 and V2 and stuff like that. Now, if we divide the whole system by G, we now have P1 over rho G plus V1 squared over 2G plus Z1 is equal to P0. This is our constant. Okay, so P0 is once again our stagnation pressure. So this would be equal to our stagnation pressure if we take into account height. If we don't take into account height, we can simplify it to just P1 over rho G plus V1 squared over 2G. Now, since it's equal to a constant, what are the units of this term, and this term if this is dimensionally homogeneous? We know that the units of this are just going to be distance. So this is meters, meters, meters. So we have an equation in terms of distance. And so what we can do is we can use this diagram and say the pressure in our system is related to the following lines. The pressure in our system is related to the height, so this would be Z2. And at point 1, this would be Z1. So you can see that the height is different. So the amount of contribution of pressure for the height, so remember we know that P1 over 2G plus V1 squared over 2G, sorry, and this is rho G, not 2G, plus Z1 is equal to P2 over rho G plus V2 squared over 2G plus Z2. So that means that both of them have to have the same exact stagnation pressure, the same exact total pressure in their system. So we now add to the system, we can add our static pressure. Okay, our static pressure is shown by this height here for 0.1 and this height here for 0.2. So the static pressure is greater in the first part than the second part. Okay, we just know that. Okay, that's what it looks like. And we can draw a hydraulic grade line that looks something like this. So we can see that there's a difference if we just take the term of static pressure and height, we actually have a difference between the two systems. Now, if we add all three terms together, we actually get a line that is flat at the top. That makes sense. We have a constant Bernoulli equation. Our Bernoulli equation is equal to a constant. So it means that if we add all three terms together, we should have a flat line, a line that shows us exactly how much the three terms are adding to. So our velocity term is dictated by this. And we can actually measure this hydraulic grade line and this energy grade line using a simple manometer assembly. So if we look at our manometer assembly, let me erase everything so that it makes more sense. We have one point here that is open to the flow. And the amount of height in this tube shows you the amount of static pressure in this system. Okay, the amount that the water goes up compared to P atmospheric is the amount of pressure that you have in the system. And if you now put the pipe directly in the flow, you now have pressure from the static pressure plus the amount of pressure that the velocity creates as well. So you can see that velocity creates more pressure essentially. It would bring the water up to a higher level. So if we add the two together, we get this whole column here, and we can add the height as well. Same thing at point 2. At point 2, we have a pressure, a static pressure that is shown by an opening at the top, plus the height of this, plus the velocity effect going all the way to the top. And hopefully this will make sense more once we do an example problem. But essentially what this means is that all three terms added together are constant throughout. If you only add two terms together, you might not have a constant, such as in the example of the hydraulic grade line. Okay, so the velocity always brings it to a flat top where the energy is essentially equal throughout. And since all these units are in terms of height, we can say that Bernoulli has a constant head. So we have a constant Bernoulli head. And we can essentially say that these three terms together, okay, so the three terms together are equal to the energy grade line on this diagram. Okay, so the next thing I want to do is to do an example problem using Bernoulli, using this, this assumption that we have a streamline flow, and we're going to be using the streamline to understand what is happening. So let me copy over the example, and we'll get started with this example. So the example says that we have a jet of alcohol that strikes a plate in the figure below. And we're told that a force of 425 newtons is required to hold the plate stationary. So this is a very similar problem to our previous example problem where we did some momentum analysis and looked at what is happening. So we have that the force here is equal to 425 newtons, and if we keep the force at 425 newtons, this system doesn't move, okay? In our previous problem, the plate wasn't stationary, it was moving, okay? It had a set of wheels on the bottom and it was moving. In this case, it's a little bit simpler. We have a stationary plate. Okay, and we're told, assuming there are no losses in the nozzle, so no losses in the nozzle, estimate the mass flow rate of alcohol and the absolute pressure at section 1. So we know that we're given a force. So we can say, as a first approach to this problem, we can say, okay, we're given a force. Therefore, we know that we're going to have to use linear momentum, we think. Okay, so since we're given a force, we know that usually we use linear momentum when we're given a force. Okay, so the hard part of these problems is figuring out when to use just linear momentum or when to use a type of flow where we look at the Bernoulli equation. And you can actually use them kind of together. So the first thing we're going to do is we're going to use a momentum balance to solve for part A. So it says to find the mass flow rate of alcohol. We haven't really looked at any other thing, and we don't really need to use Bernoulli's equation to find the mass flow rate. We can actually find the mass flow rate from momentum. So we're going to start with linear momentum, and we don't really need our Bernoulli's equation until part B, where it asks to find the absolute pressure. Okay, we haven't really found the absolute pressure in the system using linear momentum, so we believe that we're going to have to use Bernoulli's equation. Okay, so let's start with part A, where we're going to use linear momentum. And in part A, we're told we have to find the mass flow rate. So we have to find m dot. Okay, we know that the flow is steady. Okay, in the question, it says that there are no losses in the nozzle, and we're going to assume that the flow is steady. Okay, we're not given any information on flow changing with time, so we're going to assume steady flow. And if we have steady flow, we know that the mass flow rate in, or the sum of the mass flow rates in, is equal to the mass flow rate out. Okay, so the next part is going to be to figure out where we want to put our control surface and our control volume. Okay, we have to do some sort of control volume approach. So what we're actually going to do is we have some values given at D1 and D2. So we have in the diagram, it shows us a velocity 1 that is at D1 and a velocity 2 that is at D2. So I think the best thing to do is to actually use this to figure out the mass flow rate by creating a control surface that would be essentially connecting D1 and D2. And actually this should go a little bit higher so that it encompasses the whole flow of the system. And that gives us that we can find the flow at any cross section of the system. That's what we're trying to find. We're trying to find the mass flow rate at any cross section. So we can find the mass flow rate here and the mass flow rate here are going to be equivalent because the mass flow rate into our system, so the mass flow rate into our system is going to be equal to the mass flow rate out of our system. So what that means is that we can essentially write a mass flow rate in is equal to mass flow rate out and try and see if we can figure out the problem. So let's look at our mass flow rate in into our control surface. Well, we have mass flow rate in is equal to rho 1 A1 times V1, which is equal to rho 2 A2 times V2. Now, in our problem, we're given rho 1, we're given rho 2, we're given A1. Okay, we have the diameter, so we can find A1. We know that it's alcohol, so we know what's happening. And we also know that we have rho 2 and A2, but we don't have any of the velocities. We don't actually have the values of velocity. So we actually can't do a mass flow rate balance. We can't solve our mass flow rate from our mass flow rate balance because we don't have either velocity. So what we have to resort to is do a momentum balance. And the reason we want to do a momentum balance is because we're given the answer for the force. So if we know the force already, we can work backwards to figure out the mass flow rate of the water. So we have to do a momentum balance. And this momentum balance is going to happen on a different place. So let's look at a momentum balance. So I'm going to copy over the diagram again, the question again, just so that we have a clean drawing and we can sort of draw again on here. So first thing I'm going to do is we're going to do, if we do a momentum balance, we can now try and analyze our system to figure out our mass flow rate. Now, what we can do now is we can change our control surface. We can change our control volume to a different one. We're going to change it to here instead. So we're going to look at our control volume and actually move it to here because that's where the force is being applied. And we can look at, we know this is our velocity 2 coming in. So we know our velocity 2 is coming in. And now we have a velocity going down and a velocity going up. And this looks very similar to our previous example as well. So we can do a momentum balance in the same exact way as we did before. So what we can say is we have this control surface, and essentially what we're trying to find is velocity 2. If we can find velocity 2, we can find the mass flow rate, essentially. Okay, so by this system, we can call this A and we can call this B, okay, just so we have them. And we know from experience that if the flow splits along the middle of this plate, we have half the flow going up and half the flow going down. And A and B usually cancel in the y direction. So if we have a y direction and an x direction defined like this, we know that A and B are usually going to cancel in the y direction. But let's keep going with this problem and write the equation down. So if we have the sum of the forces is equal to d dt times the integral of velocity times density dv, okay, and this is our most general term, plus the sum of m dot I vi out minus the sum of m dot I vi in, we can say that that's equal to the sum of the forces. Now, we can simplify this problem by making this equal to 0 because we have steady flow. We have a flow that is consistent, so we can make that term go to 0. And so we have that our sum, if we do in the x direction, we can say in the x direction, we can say that the sum of the forces in x is equal to the force on one side, okay, which is 425 newtons. We know that that's equal to 425 newtons. Okay, we're given that in the problem, is equal to the mass flow rate out times velocity out minus the mass flow rate in times velocity in. Now, this force, is it equal to positive or negative 425? It's equal to negative 425. It's going towards the left, so it's negative. Okay, and we're told that this is equal to out minus in. So is there anything coming out in the x direction in our flow? No, there isn't. There's only a term coming in. So we can say that this is equal to negative, so there's only a flow coming in, so it's negative m dot, which is the mass flow rate we're looking for, multiplied by V2. And so we can say, going further with this, we can get rid of the negative signs and say 425 is equal to m dot V2, which is equal to rho A2 V2 squared. And so now we can solve this problem by using the specific gravity of our fluid, which is 0.79, multiplied by 998, multiplied by the area, which is pi over 4, times 0.02 squared, times velocity 2 squared. And if we solve for this, we can find velocity 2. So velocity 2 is equal to 41.4 meters per second. And now we know that m dot in or out back in our first analysis of the problem, m dot is just equal to rho A2 V2. And so we can say that now that we have the velocity term, we can find the actual mass flow rate in the system. Okay, so our mass flow rate is equal to 0.79 times 998. And 998 is the density of water. Okay, so it's a density of water from our tables divided by pi over 4. So this is in the appendix. So you can find this in the appendix. Okay, multiplied by pi over 4 times 0.02 squared times 41.4 would give you the mass flow rate, which is equal to 10.3 kilograms per second. So we started the problem with somewhat of a wrong assumption. We said that, well, it's not a wrong assumption, but it was the wrong way to try and solve the problem. Since we didn't have any velocities, we tried to solve the problem by saying mass flow rate in is equal to mass flow rate out, but we didn't have any velocities, so we couldn't really solve this problem. But we were given the force that was equal to keep the plate steady. Since we knew the force, we decided, let's make a control surface around that system and figure out what our velocity is from the force. If we were not given the force, we wouldn't be able to solve the problem. We would have to know the velocity or something else. But because we were given the force, we can do a momentum balance and figure out the velocity that would create that force. The velocity that would create that force is 41.4 meters per second, and the counteracting force would have to counteract that velocity. Therefore, from there, we were able to find our mass flow rate. Now let's move on to part B. In part B, we can say that we need to find the absolute pressure at section 1. So section 1 is right here. Okay, we're going to call this section 1. And the absolute pressure at section 1 should be found by looking for the pressure 1 right here, or the pressure in the stream, essentially. And we can think of this line here as a streamline. Okay, we can think of this as a streamline. So we also know that the pressure at point 2, so this is 1 and this is 2, we can say that the pressure at point 2, when it goes out of the nozzle, so out of the system, we can say that P2 is equal to PA. We see it right here. We're given a pressure atmospheric, essentially. So we can say, the first thing we can say is that at P2, we have pressure atmosphere, which is equal to 101,000 pascals. And from there, we're going to assume that we have frictionless flow to find the pressure. We're told that we have to solve for the absolute pressure. At section 1. So we're going to assume that we're along a streamline. And along the streamline, we're going to try and figure out the pressure. So we have P1 plus 1/2 rho 1 V1 squared plus rho G Z1 is equal to P2 plus 1/2 rho V2 squared plus rho G Z. So remember, our Bernoulli equation can be rewritten in multiple ways. So we can have it written like this, or we can have it written with, we can divide it by rho, or we can divide everything by rho G. And then it changes our equation. In this case, we're multiplying everything by rho G and having it in this form because we want it in the units of pressure. So we want, essentially, to find our pressure 1. This is what we're trying to find along the streamline. And to find it along the streamline, we're just going to apply the equation and try and understand what's happening. So the first thing we're going to do is, how can we simplify this equation? Well, we know that along the streamline, so let me copy over this diagram again so we have a clear picture of this diagram once again. So we know that along the streamline, which is in the middle of our diagram, just like this, if we look at our system from 1 to 2, we know that if we take this as z is equal to 0, we know that point 1 along the streamline and point 2 along the streamline are at the same height. So what we can do as our first simplification is say, since z1 is equal to z2, we can make them disappear. So this becomes 0, and this term becomes 0. Okay, so both terms would cancel out because z1 is equal to z2. Now, we're left with an equation that is simpler now. So we just have an equation that says p1 plus 1/2 rho times v1 squared is equal to p2 plus 1/2 rho v2 squared. So we have the term that is the static pressure in that system plus the pressure created by the velocity in the system. So we can rearrange this equation to say P1 is equal to P2 plus 1/2 times rho times V2 squared minus V1 squared by bringing the 1 to the right side, V1 to the right side. And now we know V2, we know density, we know pressure 2. Okay, pressure 2 is equal to P atmospheric, which we're given in the problem. And the only thing left to know is V1. So how do we find V1? Well, we can go back to our initial mass balance. We had said that m dot 1 is equal to m dot 2. Now that we have velocity 2, we can actually find velocity 1. So we had rho 1, a1, v1 is equal to rho 2, a2, v2. And the densities are both the same, so we can get rid of the densities. Okay, they don't go to 0, but they're the same. And we can now say it's a1 v1 is equal to a2 v2. Therefore, it's pi over 4 d1 squared times v1 is equal to pi over 4 d2 squared times v2. We can get rid of the pi over 4, okay, because they're equal to each other on both sides. And so we have that v1 is equal to v2 multiplied by d2 over d1 all squared, which is equal to 6.63 meters per second. And now that we know v1, we have all the other values, so we can just find p1 from our equation. P1 is equal to 760,000 pascals. And this concludes our problem. This concludes our study of the Bernoulli equation, and we will be looking at the energy equation in our following lecture, which will be live lecture number 3.